Hello, Mr. Sorrentino here, presenting another one of these videos for our Math 31 lecture series. And this is dealing with section 4.1, Polynomial Functions and Models. In chapter 4, we're going to explore a lot of solving polynomial equations, mainly focused around finding the zeros of polynomial functions. Because ultimately, finding those zeros is what I would essentially do to solve the equation. Because finding a zero for a function it could be the same thing, because all I need to do is take any equation and set it equal to any polynomial equation, set it equal to zero, and that will allow me, to go through procedures to find the zeros at that point, much like we did in several things with quadratic functions. And we have already studied a few polynomial functions. Linear functions are polynomial functions. Quadratic functions are polynomial functions. It's just that now when we start dealing with quote unquote polynomial functions, we're going to start seeing powers of x that are more than 2. As I had mentioned before, when we talk about graphs of anything, sometimes, when you're trying to graph things using the methods we started this course with, namely naming some numbers and just putting it into the function and seeing what you get and plotting those points, you can miss a lot of different things about a graph. So, so we had graph transformation techniques. That's why we had specific procedures for quadratic functions and linear functions. Polynomial functions, we're going to study different aspects of them, so you kind of know what to expect, what you're looking for, so that you know if you're, plotting points and you picked some x's and solved for y's, if you have enough to really go by anything. Also, these methods will also help us get pretty decent graphs of them by simply picking the right points along the way so that we can figure out what it really does look like and maybe sketch a graph of them. This also helps dealing with the calculator as well, because of the fact that some people will use the calculator to get an idea of what the function looks like, but they may not have their windows set up to see enough of it, and they start making conclusions based off of only seeing part of the graph, and that's where sometimes other errors could present themselves. So when we go over these characteristics over this in the next lesson as well, this will help us determine various aspects of these polynomial functions, so that when we're starting to determine solutions and other things from it, that we are using an entire graph of the function to make our determinations. So in your notes, you see that they do have what a polynomial function is. And basically, it's basically a function written in multiple powers of x, where you have, coefficients that are real numbers. Now, real numbers versus specific types of real numbers like integers and rationals and things like that, they'll help you determine other characteristics we'll talk about later. But the main thing that we want to keep in mind is that we're talking about instances now that, our powers are all integer powers and they're all positive. So we're not going to have any negative exponents, although towards the end of this we'll start talking about rational functions. We're not going to deal with any powers that are fractions where roots would be involved. These are very specific. As we go through this, we also want to know like what a polynomial function looks like as far as a graph goes, so we know if we're dealing with one or not. So one of the first aspects that's mentioned here is a polynomial graph is a smooth continuous graph. It has no breaks, no holes, no sharp corners. So, I'm not going to see those features on a polynomial graph. And I shouldn't see them if you're sketching a picture of one either. Another thing we discuss is what the end behavior looks like. This is very useful for determining whether or not you have a full picture of the polynomial function. As we talk about this, and I don't have it emphasized here, but it is something that's been brought up in other courses and things, that we do mention the degree of a polynomial. The degree of a polynomial, and I should say polynomial function. The degree of a polynomial function is the same thing as basically saying the highest power of, and I'm going to put in quotations, x. Whatever the variable is. We use x most often, so I'm just going to put x there. That's the degree of the polynomial. That degree tells us information. First, it tells us how many zeros we could possibly expect, and a zero The zero of a polynomial is very much like the zero of a quadratic, or, they're also known as other textbooks as roots. A zero of a polynomial is something that makes the polynomial function equal 0. So basically where it crosses the x-axis. When we're talking about the degree of a polynomial, that first could tell us possibilities about how many zeros I could expect. It also gives us an idea about the shape of the ends of the function. See, and that's what these little markings here are indicating. It means there's a whole bunch of different stuff that could be going on in between, in the middle of the function, but if I have an even degree, that means like your degree is either 2, 4, 6, 8, so forth and so on, then I know my graph is going to end pointing in the same direction. So here they're both up, here they're both down. It's up if the leading coefficient is positive, and down if the leading coefficient is negative. Leading coefficient, very misleading as far as the word goes. That's the constant multiplied to highest power of x. It's important to note it that way. Now, when we write polynomials in standard form, the standard form of a polynomial is typically written from highest power to lowest power, and that's where the word leading comes from, because this would be the leading coefficient. It's on the highest power of x that you have in your polynomial. Now, some of the functions you might be encountering may not be written in standard format, so you have to be able to recognize what the leading coefficient is. And of course, getting back to the end behaviors, if the degree of the polynomial is odd, then basically the two ends are going to point in opposite directions. And for instances where the leading coefficient is positive, it's going to be pointing down on the left and up on the right. And then that's going to be reverse if your leading coefficient's negative. So there's a lot of things that go on with this that you have to be aware of in order for you to know what the end behavior looks like. And therefore, but it's important because if you're looking at a graph of it on a calculator, let's try to get some idea of what it looks like, or you've plotted it yourself by plugging some random points in. If you're not seeing the ends look like, what they're supposed to be, that might indicate that you have more points that you need to try out, or you need to expand the window on your calculator to see more of the graph, so that you are looking at it in its entirety. So for the first example you're given, you're just simply asked to describe the end behavior, and that's by drawing that little picture of these two functions. For this one here, when I look at the f of x for a, it is written in standard form, and this is a degree 4, which is even. That means that the two ends should be pointing in the same direction. Now, are they going to both be up, or are they going to both be down? So right now, knowing it's an even, I know it's either going to be this, or it's going to be this, as far as the end behavior goes. Now, which one is it? Well, the leading coefficient's a -3, which means the leading coefficient's negative. So if it's negative, that means that the two ends are pointing down. So that means that this one here is not the right answer. It's that one. So I would expect the two ends to be pointing down. So if I were to make a graph and I don't see any indication that the two ends are pointing in the downward direction, basically where the graph goes on forever and ever, then I'm not looking at enough of the graph, and there might be other things going on that I need to be aware of. Whereas this next one, this is not written in standard form. As a matter of fact, the x's are increasing in value as I move along. So this is a degree 5, which means it either is going to look like this, or it's going to look like this, as far as the end behaviors go. I got to figure out which one it is. I'll have a lot of students that'll make the correct assumption that it is a degree 5, but then they'll tell me that the leading coefficient is 9. It isn't. The leading coefficient is 3, which is positive. And from the rules we just learned about, if it's a positive, leading coefficient, then it should start off at the left-hand side pointing down, and at the right-hand side be pointing up. So the first one I drew for this one is the correct answer. The second one's not. So that's not the correct. So those are the correct end behaviors for this. Not a major thing so far, but it is important. You're going to see its importance hopefully as we progress through these things. The next thing you're given some information about is the special names of some polynomials, because you're going to see at times they're going to say stuff about it being a quadratic polynomial or a quartic. You may see those words come up. It's important to know those particular names. Notice that the function y equals 8, which would be like f of x equals 8, a constant polynomial, it's a degree 0. That is a polynomial function. We talked about linears already. We talked about quadratics in the previous chapter. We have cubics, that's a special name. Quartic is a special name. Quintic is a special name. And you may even see these names being used occasionally in some of the problems you might be given. Usually after degree 5 for this textbook, they just simply say it's a degree 6, degree 7, degree 8. We talked about zeros of quadratics before. We want to find the zeros of a polynomial function. It's the same thing. It's basically, when I asked the question in example 2, are these zeros of the polynomial function? What I'm asked to do is determine if these values of x make f of x equal to 0. So when I'm looking for zeros so don't just think it's the number 0 all the time. I've seen students make that mistake. The 0 of a given polynomial, if I can get the right thing, the 0 of a given polynomial means I'm looking for x's such that f of x equals 0. So that's what I'll be doing in each one of these instances. I'm going to substitute the number in for the x's into the function and see what it produces. So for the first one, again, my recommendation is make sure you put when you show your substitution, so I know that you're substituting correctly, and use those parentheses as your substitution, because that should help you with the order of operations and what needs to be done first. I would take care of the exponents first in this. So, -1 cubed is -1, so the first term is going to be -2. -1 squared is 1. -3 times that is going to be a -3. -1 is just going to be, adding a -1 is going to be the same thing as subtracting 1, and I have a +6. And so I have -2 -3 -1 +6. That does come out to be 0. So the first one, x equaling -1, is in fact a 0. When I go to the second one, f of 2, did my substitutions first. I'm now going to start working these out. 2 to the third power is 8, times 2 is 16. 2 squared is 4, times 3 is 12, and I'm subtracting that 12. Plus 2, plus 6. 16 minus 12 is 4, plus 2 is 6, plus 6 is 12. That's not equal to 0, so, this is not a 0 of the polynomial. And of course the last one, I would do f of 3. So here I have 3 cubed is 27, times 2 is 54. Minus, 3 squared is 9, times -3 is a -27. Plus 3 plus 6. 54 minus 27 is 27. Plus 3 would be 30, plus 6 would be 36. So this is also not a 0. So determining whether or not things are zeros of a polynomial are fairly easy. I do show you here briefly. I'm not going to necessarily pull the calculator out to show this portion of it. However, to remind you that you could find zeros of the polynomials just by using the procedure we used before of evaluating numeric values of functions. We've done that in previous lessons. So when we talk about zeros of polynomials, or sometimes they're known as roots as well, sometimes when you're dealing with polynomial functions, especially with them, this one here, example 2, I would expect that there's 3 zeros for this polynomial function. I've only found one. I found that a -1 was a 0. And I could use that piece of information to determine what the other zeros are at that point. So, so if I could find one of the zeros, either by trial and error or just like, putting values in it and determining that one of them makes a zero, I can sometimes find the other ones a little bit quicker because I might be able to factor it out and use quadratic or linear techniques to find the rest. But at the same token, there are instances where I may have a zero that actually counts as 2, 3, 4 different zeros for that polynomial function. How am I going to know that when I see it? And that's what we got into talking about multiplicity. So multiplicity is an instance where I have zeros that count as being more than one zero. So for instance, I have this function here, f of x equals x plus 4 cubed times x minus 2 squared times x minus 5. If I would go through and FOIL this out, I would have, or do all this distribution, it might take a little bit of time, I would have a 6th-degree polynomial. And I'm just going to note that here. Now it stands to reason for this to equal 0, either this quantity has to be 0, this quantity has to be 0, or this quantity has to be 0. That's why I left it factored so you could easily see what those should be, because -4 would make x plus 4 0, and if I cube 0, it's 0, and then the whole rest of it becomes 0. 2 would make the x minus 2 in the middle become 0, and again, if I square that 0, it's still 0, and the multiplication with the other two quantities would still be 0, and of course 5 is a 0 because it makes the third quantity 0. So these are the zeros of the polynomial. The fact of the matter is, those are the only zeros, because those are the only values of x that would actually make this polynomial function be 0. But you might be saying, well, that's only 3, and this is a 6th-degree polynomial. Where do the other 3 go? Well, that's because since this was a result of cubing the x plus 4, this 4 here, notice, that's what the -4 is right here. Notice I have this graph kind of flattening out. It passes through the point, but it kind of flattens out. That's an indicator that I have an odd multiplicity, and it's more than 1. If it's 1, like for the 5, so this is the x equals -4, this is the x equals 5, it just passes through. It doesn't kind of level off and flatten before it goes through. It just goes through. So -4 has the multiplicity of 3, which means it counts as 3 zeros. That's what we mean by multiplicity. X equals 5, as we mentioned, has a multiplicity as 1, which means it counts as 1 zero. Obviously, because of the squaring on the quantity of x minus 2, that means that there's actually 2 quantities of x minus 2 involved in this function, which means those 2 quantities are where the x equals 2 is going to make this 0. That's why it has a multiplicity of 2, which means it counts as 2 zeros. I can typically tell an even multiplicity if it's an instance where the graph is what they call tangent to the x-axis at that point. That means that it does touch the x-axis but doesn't pass through. That would also hold true if it had a multiplicity of 4, multiplicity of 6. The only thing you would see differently is you would see it also flatten, but it still wouldn't pass through. The multiplicities that you're going to be responsible for in this course are typically going to be instances where you have multiplicities of 1, 2, or 3. And the graph will help you figure that out. You're not going to have to worry about multiplicities of 4 or 5 or 6, but technically you can figure out what they are along the way. But figuring out these multiplicities becomes important as we get into more polynomial equation solving later. The conclusions, which I kind of already gave for this, if c is a 0 of a polynomial and c multiplicity of k, then if k is odd, then the graph passes through the x-axis. So if it's an odd multiplicity, including 1, which is the most common one you're going to see, it passes through at that value. So if I say that if 4 is a 0 of the polynomial, I should see the graph pass through x equaling 4 on the x-axis, and it passes right through. Now, I had to judge if it's just going straight through, or if it's leveling off as it passes through and then gets steep again. That'll let me know if it's a multiplicity of 1 versus a multiplicity of 3. If k is even, then the graph is tangent to the x-axis. And both of these I should really say at c, because that's what we're assuming is the value of the 0. Circulation of daily newspapers. In 1985, the circulation of daily newspapers reached its highest level. The quartic function, so again, they're throwing out a word here, which simply means a degree 4 polynomial, which I can clearly see in the polynomial function they give us, represents the number of newspapers in thousands that are sold daily, where X is the number of years since 1940. Very important. That means if I'm given a date, I need to take away 1940 from it to get the value of X I actually use for the formula. Using this function, estimate the circulation of daily newspapers in 1945, 1985, and 2008. So you see here, you are given what 1945 equates to. That means x equals 5. What 1985 equates to, which is x equals 45. And you're also given the fact, and this won't necessarily be the case in your problems you may be given on a test or a quiz, 2008 correlates with x equaling 68. You're used this to estimate the circulation of the daily newspapers in those years. The calculations could be a little bit daunting on this one. So, and that's why I showed a calculator at the bottom of it, of the page. I'm gonna demonstrate the calculator again, just kind of reacquaint you with how to use the functions on this. And so I'm going to bring up my calculator and the detached LCD, and I'm going to put that function in here. So now I have the entire function in there. Now to talk about a couple of things, maybe I want to know what the graph looks like. And as I look at this, I notice that in my function up here, the x didn't seem to appear. So I do want to insert that here. It's the x to the fourth, not the number to the fourth. I just want to make sure to go through and make sure everything's cool with what's supposed to be here versus what's actually showing up on the calculator. There we go. Sometimes typing fast on any calculator can cause an issue. I might want to see what it looks like to get an idea of where these things will be and things like that. But I also want to do this to demonstrate, like, how knowing some things about end behavior or whatnot could help with this. So let me graph it the way it is now. And chances are I may not see much of it because this is something we set up in a previous graph. This usually means up here it's working. As long as I see that, it means it's being drawn. But right now I'm really not seeing anything. And that's because of the fact that, I have values here that are going to be in play that I may not be able to see. I mean, heck, I have x values that go to 68 for this. I don't know how high up. I mean, this is going to be in thousands in the long run. And the fact of the matter is, with the constant term itself being 41,334, which means that's 41,334 thousand. So you're talking about having, thousands, which is a million. So that's 41, 1,334,729 approximately. You need some rather big numbers on the y's. So I'm going to adjust my window accordingly to make it fit better, maybe. I know I want to go from, maybe have something over here like, in the negative so I can see my axis. But maybe I'd like to go to 70 to see what goes on with my x values. I don't necessarily want to go by ones because this is going to, make my axis look kind of yucky. I'll go by tens. My y min, I might want to go maybe, like, let's say maybe negative 1,000. But maybe for the sake of argument for this one, just let my y max be maybe 50,000. Might want to see more of it later. And I just go by thousands. See if that does any good. And as you can see, I mean, I see parts of the graph here. And the question is, was that a good enough part of the graph? Well, I know that I'm missing some stuff up here. It is pointing on the left-hand side down, and it seems like it's pointing down on the right-hand side, which means we have a good range of x values here. Because the end behavior tells me, since it's an even degree polynomial, they should be pointing in the same direction. And since this is negative, it's pointing down. So I have enough of x coordinates here, but there might be some other thing going on up here that we haven't talked about how to find those yet. So I might want to make my window go a bit further. Maybe make this 100,000. And maybe make this go by 10,000s instead. As I said, if you know some of the features about graphing, you might be able to figure out, if you're seeing a good enough picture or not. And it seems as though that even though it's quartic, and sometimes in the middle, I could expect to see possible more fluctuations that I see here. This looks almost very parabolic, and that's pretty good. That means it's a decent function. I can also now trace to figure out what these things are if I needed to. So having that in there lets me look at some graph behavior. And I can also see here, it looks like, when my x values, which are going by tens down here, when x is about, 40, it seems as though that's when I'm going to reach about a maximum as far as circulation goes. So as I look at this, when x is 5 in 1945, I expected it to be a certain value over that initial 41,000. In 1985, which is 45 years later, I would expect it to be kind of where its maximum is. And so I should see a higher value for its readership. And then in 2008, I should see it be down a bit more because it should be somewhere around here. So that also lets me kind of anticipate what the answers may be and how they should look when compared to each other. So as far as evaluating them go, especially when you have a lot of nasty decimals in here, if you have some really nice integers or some doable fractions like 1/2 and things like that, then by all means you should try to do it by hand first and then use the calculator to maybe check. For ones that you have nasty decimals like this, I'm going to say you should really use the calculator to help you. And the biggest part was typing it in, because now all I need to really do is just go to variables, go under Y variables, and choose Y1 because that's where I type that formula in. And so if I want to see what happens when x equals 5, I'm just going to put in parentheses 5, and that's the readership. Now remember, this is in thousands, so that's 48,277,000. So I would say that's about 48,277,000 readers for the newspaper, if you round it off to the nearest, nearest whole. For 1985, scooch this over a little bit, bring these guys back up. If I hit second and enter again, it brings back the last thing I entered in. So I don't have to worry about going through the entire menu to get that Y1 back. I just change that to a 45. So in 1985, when x is 45, that readership is 61,897,000 readers, or 61,897,000 readers for this circulation of this newspaper. And then lastly, when I look at this x equaling 68, which I see is over here, which is what corresponds to 2008, again, I can just replace this with a 68. And as I mentioned, I expected to go back down again. It did, which means this would be 48,836,000 readers approximately with this newspaper at that time. So that's how your calculator could help you with that, and how some of the graphing techniques can help you figure out what's going on with it and know what to expect for right answers and so forth. 4.2 Graphing Polynomial Functions. So we talked about some of the features of a polynomial function in the previous section, 4.1. Really not enough though to help us graph it, because graphing, it takes you to like know specifically where certain things are going to occur, and until we get the idea of what to look for, it makes it a little bit more difficult to graph them accurately along the way. So we're going to just find a procedure here that there's certain things that we need to find, and those things will help us determine not only what points to determine what the graph looks like, but also how to scale our graphs and things of that nature as well. So one of the first pieces of information that they go into is that they tell you if you have a polynomial function of degree n, and basically that polynomial function will have at most n zeros. We talked about that in the previous video. If it's a degree 3 polynomial, I would expect to have 3 zeros. If I have a degree 8 polynomial, I should expect to have 8 zeros. Some of them might count more than once. Some of them might be non-real, as we'll talk about as we move on a little bit later into this chapter, and they won't be represented on the graph. But it's important to know that that's how many I would expect to see. We start talking more about the turning points, which are known as critical points in our textbooks, particularly in calculus, which are basically your like maximum or minimum. It's basically where the graph kind of tops out and goes back down again, or bottoms out and comes back up. It may not be the lowest or highest point of the graph, because there might be other places where the graph goes higher, but it is represent where these things turn. And so if I have a degree n polynomial, I would expect to see at least n, or I would expect at most n minus 1 turning points. So again, if I have a degree 5 polynomial, I would expect to see as many as 4 places where the graph goes from increasing to decreasing, or vice versa. Those are also important to assist you in graphing as well, because we mentioned before the end behavior can help us with that, because it'll let us know if we see enough of the picture in front of us. But also, once we determine that, from the end behavior that I'm seeing what's going on, if I'm not seeing what I would think would be enough turning points, then I have to consider that there might be something else going on as well, or I'm not looking at enough of the graph, or I'm not setting up a good graphing region to see everything. So that becomes important along the way as well. So when you graph a polynomial function, the following is the procedure that we're going to tend to focus our attention on to do it. In order to graph a polynomial function, we first want to determine the end behavior like we did in the previous one. That says 3, 1. It should really say 4, 1. The next is to find the zeros of the function. This can be somewhat daunting, and we haven't by this point talked about all the ways of doing this yet. So we're going to start off with some ways where we could use some factoring, and the factoring is pretty obvious, but as we move into this chapter some more, we're going to deal with circumstances where the factoring is not as obvious, and we may have to use other methods to determine how to find these zeros. We want to use the x-intercepts to divide the axis into segments, and then use substitution to determine if the graph will be above or below the x-axis. And I'll show what that means momentarily. We want to find f of 0, the y-intercept, and that's pretty easy, because all the x's will become 0, and you're left with a constant term. Find additional function values to determine shape. That's kind of vague, but once you do those previous steps, you should have an idea of which values of x you might want to explore a bit more and find their values, so that you have a good enough set of points to graph. And I want to be aware of the number of turning points to expect and the multiplicity of zeros along the way. These are things I have to consider as I work through this. So let's apply these to an example now. So we're asked here to draw a graph of the polynomial function f of x equals negative x cubed plus 2x squared plus 4x minus 8. So I'm going to go through the list that we just established in the previous part of this video and come up with needed things to help me graph this thing. So first of all, I want to talk about the end behavior. The end behavior comes from me knowing the degree of the polynomial and the leading coefficient. So I know it's a degree n, or degree 3, which is odd. And I know that the leading coefficient is -1, and that's less than 0. So having an odd degree means that the two ends should point in opposite directions. Having the leading coefficient be -1 means that the end behavior should look more along the lines of this. So I know what the end behavior is going to look like. So overall, the graph is going to end with the left side pointing up and the right side pointing down. Now I want to find the zeros of the function. The zeros of the function could be a little bit problematic because of the fact that there's different techniques we can use to find this, but they're all going to revolve around some factoring first, because we don't have a set formula to handle degree 3, degree 4, degree 5, so forth and so on polynomials. We have methods of solving linear functions. We have methods of solving quadratic functions. What I'm ultimately going to be needing to do with anything over degree 3 and over is finding a way of factoring it down into linear and quadratic functions or expressions so that I can handle those using methods we've learned in previous chapters. So when I look at the function f of x, and I'm going to work with it over here, if I'm looking for zeros, I'm going to set the function equal to 0. Which, is one of the methods we tend to most often use with a factoring method. So, because I like to get this set into factors where I can determine that, okay, with these being factors of this polynomial, I can, have this as a multiplication of factors, and by the zero product property say, well, if this product equals 0, then one of the parts of this product also has to equal 0. Now, when I look at this, we don't have like specific techniques for factoring, cubic functions. We had, some methods of factoring. Some of them you learned in the high school level math you may have taken. I talked about the AC method of factoring quadratics before. We have those for quadratics, but not necessarily these. So sometimes you have to, look at them and have practiced these enough in order to find out some of these things. But one of the things that I notice about the function f of x is that it does have 4 separate terms. -x cubed, 2x squared, 4x, and -8. Those are all the terms of this polynomial function. Anytime I have an even number of terms, I can attempt group and factor, which is something we did use when we were talking about using when we were doing the AC method. We eventually split up the middle term into 2 separate terms so that we had 4 terms and could use grouping and factoring. So I'm going to attempt that. If you attempt grouping and factoring with polynomial functions, it may or may not work. If it doesn't work, that doesn't mean there may not be anything you can find. You just might have to use another method. But this one's going to work for us. So luckily, we have that. As we go into other functions and other parts of this chapter, we'll look at other methods of doing that. I'm going to look to see what I can factor out of each one of these groups. Out of the first group, I can factor out an x squared, and then more importantly, I'm going to factor out a -x squared. I always like to have my leading coefficient or my highest power of x in any quantity be positive. So I'm going to factor out a -x squared, which means inside the parenthesis I'm going to end up with a positive x, and I'm going to end up with a -2. When I factor the second group, some things I'm looking to have happen. One, I want to factor something out of both terms. And 2, I'd like to have that quantity of x minus 2 happen again. And it happens to work here. If I factor out a positive 4, I do end up with x minus 2 in here. Because 4 times x is 4x. 4 times negative 2 is a minus 8. And so what I have here is I can factor out the x minus 2, and I'm left with negative x squared plus 4 equaling 0. So now I have this factored into quadratics and linears, and by the zero product property, either x minus 2 has to be 0, or negative x squared plus 4 has to equal 0. The x minus 2 equaling 0 is an easy one to solve. I add 2 to both sides, x is going to equal 2. So x equals 2 is a 0 of this polynomial. Negative x squared plus 4, if I subtract 4 from both sides, multiply both sides by negative 1, and then square root both sides, I get that x is going to be plus or minus 2, which boils down to this saying x equals 2 or x equals 4, or x equals negative 2, sorry. So some important things happen here. When I went through the solution process, you notice that the x equals 2 showed up twice. This means that x equals 2 is a 0, but it has a multiplicity of 2. Whereas x equals negative 2 is the other 0. So I know I have coordinates 2, 0 and negative 2, 0. Notice I am not graphing anything yet, because I have to first figure out other things about this particular function and know how far to scale it. So I'm not like immediately putting these numbers in yet, but these are numbers, I'll put some stars next to them, that I'm going to eventually want to plot. Now, when you get to step 3, we have these x-intercepts. We want to be able to divide the x-axis into segments and then use substitution to determine if the graph will be above or below the x-axis. So I'm going to call this test above below. And as we get into some other things eventually that we can actually find with polynomial functions, some of these can get replaced or streamlined together with something else. So I'm just going to set up a little number line here, just kind of keep track of where the x-intercepts are. We have negative 2 and we have 2. And much as I did before, and now I know these are zeros. I want to get an idea if the graph is above or below the x-axis based on what numbers I plug into this. So for instance, between these two numbers, the number 0 would be between them. I want to know, okay, between negative 2 and 2, is the graph above the x-axis or below the x-axis? So if I do f of 0, I'd work that out and get that it's a minus 8. Pretty simple to use because of the fact, and this is also part of the next step, we do want to find the y-intercept. So as I said, some of these things you're being listed here, you can kind of kill two birds with one stone in some of them. So I know that f of 0 is equal to negative 8, which means that 0, negative 8 is also another point on the graph that I'm going to plot. Knowing that f of 0 is negative 8, that tells me that at 0 I'm below the x-axis. So between negative 2 and 2, I'm below the x-axis. when I put in 2, and I do f of 2, no, f of 2 would be 0, so if I pick another number that would be in this region, we'll say 3, f of 3, well, I'd put that in my calculator and compute it. And when I do that, I get a -5. Which means that after the 2, so between -2 and 2, I'm going to say it's below the x-axis. After 2, it's still going to be below the x-axis because f of 3 is -5. And if I pick a value to the left of -2, say -3, and I do f of -3, and put that in my calculator, I get 25, which means it's above the x-axis. The cool thing about doing this is also has given me additional points that are on the graph, because this indicates here that I have a point at 3, -5. This indicates that I have a point at -3, +25. So that has given me the points on the graph. So with this information, I might actually have enough to plot this. Let's see what it looks like and determine if we need any more numbers. So as I graph this, I'm going to use the blue. I'm going to go a little thicker on this. Now, so far, I know I had to fit at least up to 25. So if I scale my graph, which is going to be something I want to do first and foremost, I want to scale my graph. It looks like, since a lot of the stuff that's going on here is happening between -3 and 3, if I go by ones on my x-axis, that looks like it's going to be good enough. So 1, 2, 3, 4, make -10. I already have a y value appearing in an ordered pair of 25. So I might want to make it go a little bit beyond that. I mean, because I don't know where the maximums and minimums are going to be, yet. But I at least want to go up to 25 at this point. So maybe go up to 30. So maybe let each one of these, let's let each digit be 5. So this is, so you have to be able to do some of this stuff on your own without the use of the calculator, aside from using it maybe as a computational tool. So, so plotting some of the points that I do have at this point. I have this 0, -8. And I'm going to have to judge where that is. I mean, I would say it's roughly about here. I have the two zeros. I have 2, 0 and -2, 0. So 2, 0, -2, 0. I have the point 3, -5. So 3, -5 would be right here. And I have -3, 25. So -3, 25 would be right here. Based on what I'm seeing with the graph so far, it looks like it's going to do something along the lines of this. Which certainly does account for the multiplicity of 0, or the multiplicity of 2 at 2, 0, because it's touching the x-axis but not passing through. Looks like I do have like a lowest point around that 0, -8. So I have an idea what the shape looks like. Maybe I want to find an additional point over here so that I'm being more accurate, because I mean, at least I had a point over here that I can say, okay, that left-hand side's doing that. I know I'm seeing enough of the graph because the end behavior is behaving like it's supposed to. The left-hand side's pointing up, the right-hand side's pointing down. I have all 3 zeros represented because the multiplicity of 2 means that one of them counted twice, so I do have 3 zeros here. I do have what looks like 2 turning points shown here, and I should have that many for this. So really the only other point I might want to have is maybe find out what's going on at 5, or somewhere in that neighborhood. So maybe doing one more and do f of 5. to see what we end up with. And when I do that, I get a negative 63, which indicates, well, that's going to be a point at 5, negative 63. Which kind of falls off where my graph is. I mean, I would probably have to guess that negative 63 would be somewhere like right at the edge of what I could show you here. Maybe then I'd say, okay, well, let's just try to see what happens at 4. So at least I have one other point to go with. So if I do the same calculation at 4, I get negative 24, which means I have the point 4, negative 24. And so I could plot that point now here and say, okay, 4, negative 24 would be roughly about here. And so now when I want to graph this, I can say, okay, it's probably looking at something along the lines of this. And then remember, I want to be as accurate as possible, but I'm not plotting as many points. But notice how the end behavior worked its way in here, knowing some factoring worked its way in here, determining parts that are above or below the x-axis worked its way in here. And generally, that's what the graph looks like. I could, to verify at this point, I could show you what it looks like on the calculator. And since I have a good idea of the window I've used on this, I can make a very similar window on my graphing calculator. So let me pull that up. And now, knowing that I set up a window here for my graphing window that goes from negative 10 to 10 on the x's, negative 10, 10, and I went by ones. I let my y's go from negative 50 to 50, and every 2 spots I went was 10, so that means that my scaling I went by 5s. In reality, I could also make it go by 10s as well. Now when I graph it, it should look like this one. And now see, the only difference is, like here, I could see that 0, negative 8 I kind of looked at as being the minimum, whereas the minimum looks like it's a little bit lower than that. So, but overall the graph is pretty accurate. That's good enough. And as we go into more techniques of dealing with the function and finding things about the function, we'll be able to produce even more points for the graph along the way. So we'll certainly make it even more accurate as we go along and find other things about it. Which brings us into another theorem that has its uses. We don't use it very specifically. We kind of use the concept of it as we go through other parts of this polynomial graphing process, but it is kind of important for us to mention it and talk about what it says. So let's have a look at it. The theorem is known as the intermediate value theorem. It's helpful in some ways when you're trying to think about, finding points on the graph, and it kind of relates to that above and below test that we were doing beforehand. But the intermediate value theorem says this: given any polynomial p of x with real coefficients, so we're talking about that all the numbers in front of the x squares are real numbers, and that a and b are real numbers, so a is less than b. If p of a and p of b have opposite signs, then there is at least one real value c that's between the two, and the polynomial is 0 at that value. It basically is telling me that, if I put in a value in a function and get a positive number, and go up maybe just go up 1 unit and say, okay, if I have f of 1 is 4 and f of 2 is negative 3, that means that somewhere between those two numbers, the graph has to pass through the x-axis, and therefore it has to have at least one spot where it has a 0. So this is kind of a roundabout way of locating zeros and doing it kind of more of a graphical way. So we don't use it directly, but keeping the idea behind it helps us realize, okay, well, I know if I'm above the x-axis here and I'm below the x-axis there, then I have to pass through it somewhere, okay? So this could also be helpful for us finding it. So for instance, if I'm looking at example 2, it wants to know, is there a real 0 between x equals 1 and x equals 2 for this function? So the only way I'm going to be able to do that is to actually calculate those out. So let's calculate f of 1 and f of 2. So I calculated these two values out. And what I see here is at f of 1 I was at -4, at f of 2 I was at positive 51. There's a sign change. And that allows me to say there is at least one real zero of f of x between x equals 1 and x equals 2. It doesn't tell us what that zero is. It doesn't tell me if there's even more than one zero between them, which could be a possibility. It just means that I should be focusing my attention on that region of the graph to see that I should at least be able to find a zero there, maybe more. And I could also need to find out a way of determining what the value of that zero is. When I look at B, is there a real zero between 3 and 4? So I still have the same function. I'm going to rewrite it for our purposes here. I'm going to do f of 3. I do f of 4. So for this, I have no sign change. Theorem. If I have a sign change, that means I have at least one zero. If I have no sign change, all I can really say is it's inconclusive. I could say there's no evidence, but I cannot say no. I don't have evidence that there is one, but that doesn't mean there may not be one. And the reason why it's important to note that is because maybe I picked two numbers that are too far apart. Maybe what happens with the graph between 3 and 4, although having a big number for f of 3 and an even bigger number for f of 4, it's less likely. But say at 3, it was up here, but it may have went through, came back up, and I'd be up to here when I got back to f of 4. There could have been a lot of stuff that goes on between those two numbers. So, I could actually have 2 zeros or 3 zeros, but there's no sign change to let me know, okay, to look for one. So that's why the intermediate value theorem, it has a use in like kind of thinking about like one way of locating zeros. And it is a premise that the calculator uses when finding zeros, the method we've shown before, because that's why I had to pick an x min and an x max, or your left bound and right bound, because I wanted to pick values close enough together that I would get a sign change, still get a sign change, and that'll help me locate where the zero would be. But if I have two values where I have two places or more where the graph crosses the x-axis, I could fail this test, but still in fact have zeros. I just don't have the evidence to say one way or the other. So that's the issue with the intermediate value theorem, because the intermediate value theorem either allows you to say definitively, yes, there's at least one zero, or I don't know. And so that brings me to the end of 4.2's video. If you have any questions regarding this concept or anything else we've covered so far, please make sure to come to my office hours or bring them up in class. Until I see you in one of those locations, or until the next video, I will see you around. Have a good day.